Okay, what I have in my hand is a switch mode power supply board. Okay, so as you can see, you know what? Let me rephrase that. Okay, what I have in my hand is a picture, a drawing of a switch mode power supply board. It's not an actual board. I need to clarify that because I know I'm gonna have some friends and family members watching my videos, and they're gonna say, "Hey, big dog, in the beginning of that video, that whiteboard that you was holding in your hand, what that go to?" So I already know, right? So just. Okay, so basically our power supply board is broken down into parts. It's actually 5, we'll make it 6 different parts. And so if you want to know how a power supply works, you gotta know how it works, right? Okay, so if you want to know how to troubleshoot or repair it, you have to know how the power supply performs. And this switch mode power supply performs in almost every single unit that uses a power supply electronic device there is. Same method, same operation, right? Okay, so first stage is our EMF, as our filter and protection circuit, or EMI filter, electromagnetic induction, okay, for the line voltage that's coming in from the wall. Okay, so let's break it down. Okay, so first comes in, the AC signal comes in through here, goes through a fuse. It's a big ass fuse, ain't it? Okay, goes through a fuse, right? And then we go through a protection here. It's called MOV or a Varistor, okay? And basically what this does is when your AC comes in, let's start from the beginning. The electric company supplies voltage to your home. AC is more economical to use AC than it is to convert to DC and then send it to your home. So it's basically more efficient for them to send an AC signal, which is alternating current, okay, into your home, right? And then the actual device, TV, computer, DVD player, whatever, electric stove or whatever, is going to convert the AC into DC, okay, using a rectifier circuit right here, or rectifier diode. But the AC comes in, okay, goes to the fuse, okay. This here, I'm going to just show you here. Okay, on this power supply board, same thing. This here is usually blue, but you can tell by the material. It's not a capacitor. This is a capacitor, but it's not a capacitor. This is what they call a Varistor, or MAV, metal oxide Varistor. Okay, and basically what that does, supposedly, right? Let's just say we got 120. Okay, so we got 120 positive, 120 negative. It's doing that 60 times per second because we're at 60 hertz. Okay, it's going up and down 60 times per second, correct? So what this is going to do is, just in case you get a spike or surge on the power line, let's just say the cable guy working, in the house a block away or whatever, and he drops his pliers onto the transformer for electricity, and all of a sudden your 120 jumps up to let's say 350 or 250, whatever. It's going to try to clip it. Okay, clip it here for however long it takes, how many seconds, whatever, the voltage jumps up. Okay, if not, if it's too high, it's going to short, okay, and it's going to blow out the fuse, okay, because remember, current goes to the least path of resistance, okay. So, all right, anyway, so, like I said, this is your MOV here. On this one, on this board, here's another one, right here. Okay, metal oxide Varistor. Okay, that's this right here. Okay, then we're gonna go through a filter circuit because your AC that's coming in still has ripples in it, right, around the edges. So between these capacitors and both of these, this is a dual filter, and these coils, okay, or line filters or whatever you want to call them. They're actually just 2 coils on each side, here, another capacitor here. It's going to take those ripples off of the AC signal and make it a cleaner AC signal to be rectified, right? Same thing. Let's see here. Is our power? Everything's about a power cord, fuse, varistor. Okay, then we have 2 filter capacitors right here, and our 2 inductors. Okay, to help filter it. And then the next stage is always going to be the AC to DC. Okay, rectifier, and that's right here. All-in-one rectifier diode that converts the AC into DC, so the rest of the TV or the rest of the device can use the DC for the 5 volts, 12 volts, whatever. Let's look at this one. Let's see here where we at. Power cord, power plug, MOV, middle oxide varistor. Okay, that should be reading open at all times. It should not be reading it short. Okay, capacitor, inductor or line filter inductor, another capacitor, inductor, and then boom, right there. There is our, that is our diode, rectifier diode, okay? All right, so real quick, DC, okay, once it gets through there, there's DC voltage here coming out of the diode, okay? Then, use what they call a power factor correction circuit, okay? So what happened is that all that is going to boost that DC voltage. Let's say the voltage is 125. It's going to boost it up to about 250, 300, or whatever it needs. Basically, all this is a power supply within the power supply. Okay, so it's going to take advantage of the voltage here, and it's actually going to boost it. So when it gets to this point, instead of the 130 volts DC or whatever you're going to get right here, it's going to be approximately 300 to 400 volts. Okay, depending on what the device needs and the way it's designed. Okay, so that's what we call a power factor correction circuit. It's more of a, like I said, it boosts the circuit, the voltage up. It's a booster, and also it helps to regulate the voltage here also, okay? All right, and then we have a filter capacitor, a big filter capacitor, which is usually located here. As we see on this one, right here, this uses 1. This one uses 2, okay? All right, so we got the rectifier stage, our diode right here, bridge rectifier. Okay, now just so you know, some devices may not use this all-in-one bridge rectifier. They may use 2 diodes or the 4 diodes for a full bridge rectifier. But this is all-in-one. It's what they use on most modern TVs. This is the all-in-one rectifier, which looks actually, this was bent over up under the heatsink, but like this one here, okay? This one right here, okay? Once again, AC, fuse, MOV, middle oxide varistor, line filter and line filter capacitors, and filter coils, and then boom, right here, okay? All the same one. It's about every power supply board. All right, so we'll get past the PFC circuit, okay? Filter capacitor, and then that's what's going to essentially, maybe another fuse here. Oh, I forgot about this right here. This is I'm sorry, I'm getting ahead of myself. This is another device. It's called a thermistor, or NTC, right? And basically what that does, these here, actually we got 2 here, maybe use 1 or 2. It doesn't matter where this is at, but it's always before the diode. So it could be here, it could be here, but that's just to protect over current, over voltage protection, over current protection. And basically all this is a resistor that actually increases resistance as it heats up. Okay, let's see on this one right here, we have 1, where are we at? Right there. There's 1 there, okay? Right after the coil, after the power line filter, right? After the line filter, they're here. And that is connected in series with the rest of the circuit. And that should be reading short, okay? If it's open, replace it. If it's open, check for a short on this diode, or anything else shouldn't be shorted here. These capacitors might short out, but I doubt it. But yeah, if that's open, replace it, okay? Some TVs use a resistor, a fusible resistor. Most TVs use this. And if I was to check this, if I was to take my hot air gun and blow hot air on it for about 10 seconds. And I was going to have my meter on these two leads in the resistance scale. You're actually going to see the resistance go up as I'm heating it up. And when I remove the gun, the resistance is actually going to go down. I'm not going to show you on this video because it'll be too long. So I just want to get through the basic stuff. Okay, so let's get real quick now. So we're going to go to the filter capacitor and our transformer. Okay, our switch mode transformer, or what they call a chopper transformer. All right, right here. And that's the primary winding, and this is the secondary winding, the cold side. Okay, and also we have a feed, so it's our 5 volt standby, 3.3 volt standby, whatever voltage it's supposed to be, whatever power supply board. It always has a feedback circuit using a optocoupler. All right, so this one, you see we have 2 here. These are optocouplers. Okay, that was what provides feedback from the secondary side to let the primary side know what's going on. Okay, there's a short here, it's going to cut the drive circuit off or whatever. Okay, all right. So with that being said, another thing to notice is that the switch mode power supply is always isolated. There's always a line separating the hot side from the cold side. Okay, same here. There's a line separating the hot side from the cold side. Okay? All right, so the hot side is always the side, or the primary side, what they call it hot. See, it has marked on the board also, and most boards, cold, hot. On this side of the line here is where the power cord is. It's always on the hot side. The power supply, I'm sorry, the AC and the fuse and whatever I just showed you. Okay? All right, so here is a power supply board. I think this is good. It's out of a 75-inch Samsung. Okay, as you see, it's bigger. So, like I said, according to the specifications of the device, it's how big and how many more components are going to be used on the power supply board. So anyway, as you can see, this is our power cord here. Okay, our ACN. All right, and I'm just going to show you. All right, we have our fuse. Let's see if I can do it this way. Okay, so we have our fuse. Okay. Live wire. Okay. Fuse. Across the fuse here. Across the fuse. Okay. Good. And then this is our fuse. This is our MOV right here. As you can see the symbol. This is a symbol for MOV. It's a little 2 arrows pointing toward each other. Okay, that should not be reading short at all. Okay, so still on this side here. Okay, going through our first coil. All right, it looks like it's separated, but it's not. There's a coil on this side, there's a coil on the negative side. As you can see, the other side of this transformer right here, or line filter, I'm sorry, right here, is, okay, but anyway, that's going to the neutral side, right, of the wire, and this side, the live side, is going to the other side of the wire. Okay, now if we're not getting the voltage here or not reading continuity, you have a blown fuse, most likely. Okay, all right, going to go to the other side. Okay, going to come down. All right, now this here, right here, now this here is our thermistor. Okay, they're actually using a resistor. Okay, so that should be reading close to 1 ohm. Sometimes it could be 10 ohms, but it's reading about 3 ohms already. Okay, but anyway, we'll go across here, and then boom, our first filter right here. Okay, okay, going across our first line filter here. There's a coil on this side, and there's a coil on that side. All right, as you can see, coil on this side, the neutral side and a coil on the live side, okay? So to make sure that we have continuity, once again, I'm going back to my positive or live wire, okay? And it's going around here. So this side should still be negative, okay? So this is where we at. That's our negative side there, okay? And this is our positive side on this side of the transformer, okay? Transformer, and the other is the second line filter, and that's going right to here. Well, I got a circle. That is our bridge rectifier circuit. Oops, I'm sorry. Where are we at? Where are we at? There we go. So that positive wire, the live wire or the positive, ACN where the fuse is at, that should go all the way, reading continuity, no more than 10 ohms, all the way up to the bridge rectifier diode, which you see here. Okay? Same concept once again. Here is our ACN, fuse, line filter, okay? Filter capacitors, there's one here, there's one there. Okay, our thermistor is actually using a resistor for the thermistor. Okay, that's our MOV, metal oxide varistor. Okay, that should be reading open, right? That is reading open. Okay. That should not be shorted. Okay, only thing that should be reading short is this resistor because like I said, it is in series, okay? And then all the way up to our bridge rectifier diode, okay? So after the diode, all right, that's what the voltage is being converted from the AC voltage being converted to DC, all right? There's actually 4 diodes in here. That should not be reading short at all, okay? There should be no shorts at all. If you're reading a short there, check back. Check back through these line filters. Where am I at? Oh, up here. Okay, I'm sorry. Check back through these line filters. Make sure this MOV is not shorted. Varistor. And there could be something shorted after the fact on here. So let's keep going further. As a matter of fact, let me just show you on my meter how we should check this. All right, anytime you use a power supply board by itself, always make sure that you are using a isolation transformer, okay? All right, simple isolation transformer I picked up on eBay for about, I don't know, 50, 80 bucks, something like that. Okay, it's got two plugs, right? So that way it can keep you and your equipment safe. You may still get a shock if you touch these capacitors, okay, or anything else on the board. So just be very careful when you get the board plugged in. Okay, so what I'm going to do now is I'm actually going to plug the power supply in, board in. Okay, now before I do that, people have always been asking me about how do we know if the power supply board is bad or if it's the main board. Let's say, for instance, you have a dead set. Okay, that's the reason I'm making this video, for a dead set, which means there's no light on the front. The TV does not come on at all. It's as if the TV is unplugged. That's the symptom that you're going to be getting. A dead set. No power, no standby light in the front, no clicking, no picture flash you're turning on, nothing, just dead. All right, so this is how we're going to determine that. And this is how I do it, okay? On a dead set, the first thing you want to do is check the fuse, okay? Fuse is good. See? Fuse is good. All right, now, like I said, on a dead set, the fuse is good. No one to isolate the power supply from being bad or a bad main board. Is we jump all the way across the whole circuit and we check our standby voltage, which is on the cold side, the secondary side. Okay. So I did see something here with a standby thing on here. Let's see here. Here we go. Okay, this is all hot. I'm sorry, this is all hot side. This is our secondary side, as you can see, cold side, okay? And anytime you're making voltage checks on the cold side, you can use anything metal on the TV. You can use the metal part on the jack panels. You can use the metal chassis inside of the TV, whatever. You can make a heat shield covering the T-con board, you know, as long as it's screwing into the chassis. That's where you put your ground lead. So like I said, on the dead set, the fuse is good. I'm going to go right here, go all the way over, put my meter on DC volts. Okay, and I'm going to check for standby voltage. Now, if you want, you can go to the plug right here. Okay, as you can see, this is our cold side, separated by this line here. All right, so these are all our output voltages, and this is our pin, our plug that's going to the main board. There should be a standby voltage there. It says standby at that plug, 11.8 volts on when the TV is on. But if it should be a standby if it's not on. But this Samsung actually uses actually grounds the power on instead of putting a plus 5 volts. And so we should be getting, since it's unplugged from the main board, we actually should be getting around the 12 volts. So let's see. I'm gonna put my meter on DC volts. I'm gonna plug it in. I'm sorry. Let's plug this in. Make sure, look up under the rubber, make sure there's nothing metal up under here or anything. Okay, so let's plug the AC in. Okay, be very careful when you're doing this not to try to touch too much. All right, so I'm gonna go all the way over here to where it says standby. Where we at? This pin right here. And I'm going to find the ground. Okay, I see some metal here, right there. I'm going to use ground my meter there. I'm going to put it on here on the pin, on this test point where we at. Okay. Just wanted to close in so you can see what's going on. Okay, ground, standby. Look at my meter, and boom, 12 volts. Okay, so the reason reading 12 instead of the 7 volts is because the TV is unplugged from the main board. So no big deal. We got 12 volts there. Okay, it said 11.8, but we'll just say that's close enough. 12.8 for right now. Okay, now if we have voltage there, whether it's 5 volt standby or 3.3 volt standby, which is normally the case in most TVs. If the fuse is good and we have standby voltage here and we still have a dead set, the TV is not, like I said, showing no signs of life at all, no light on the bottom or anything, then we know we have a bad main board. Okay? Because the power supply board most likely is working. Now, if we have check the fuse and it's good and we come here and do not get standby voltage, then we know the power supply is bad. Okay, we have to work our way back. Okay, we have to work our way back, all the way back here. But the best thing to do is, first of all, make sure, let me unplug this. Okay, now these capacitors still have a charge on it after you plug it in. So just make sure, I'm actually going to grab it from, I'm trying to do here, because I'm probably going to get shocked, but all right, anyway. So this is what we have to do here. All right, we're going to go straight to our bridge rectifier diode. Okay, right here. Okay, turn it back over. Right here. Okay, matter of fact, I can do this while the TV is facing this way. All right, the board is facing this way. I can do that. So next we're going to check. I'm going to plug it up again. The 2 pins on the inside should be the AC, and the 2 pins on the outside should be DC. So first of all, let's go with the AC. We're AC volts. All right, we go to the 2 pins in the middle. Doesn't matter which way, it just should be AC volts, 120 or 119 or whatever it is. It should say AC here. Okay, AC. Did I plug this in? Hold on, wait a minute, what's going on here? AC voltage. There we go. 120 volts AC. Okay. Now the two outer pins are going to be DC, supposedly, right? Got my meter in AC, still. You see it's fluctuating, okay? So I'm gonna put my meter in DC, all right? We'll go to the two pins on the outside of the bridge rectifier diode. Those should be our output DC pins. Come on. 124 volts DC, okay? We'll go back. We can't check DC. Let me see if it's going to read a reading on. Yeah, see, there's no DC here. This is AC on the two pins in the middle. But the two pins on the outside, just got my meter, my leads reversed. Okay. That is DC. Okay. Now, I'm going to show you something. Okay, so that's working, right? Okay. If we're not getting the AC voltage input, then that means there's something wrong behind here. Okay. I mean, there's something wrong. Maybe one of these coils are open. Maybe this is, I'm sorry, maybe this is open. Okay. Fuse could be open also. But as long as we're getting AC in and DC out of that bridge rectifier diode right here, we're good so far. Now I want to show you something. You see how we're getting, okay, we're in DC, 124 volts DC at the output of the bridge rectifier, okay? I'm gonna go to the capacitor, right? Now, whenever you're using ground, whenever you're checking voltage on the hot side, you always want to use the negative part, the negative side of your big filter capacitor or anything that's connected to it, okay? However, before you get here, when you're checking AC, the AC line before it gets rectified, you always want to use the neutral side of your AC in, right? Okay, so you cannot put your negative lead on the capacitor and then check voltage across the fuse. No, you have to go here and check AC voltage across the fuse and keep going like we just did, okay, an AC. Once we get past this bridge rectifier, we're gonna have to use, we can use the negative side of this bridge rectifier and check voltages, or we can use the negative side of the filter capacitor, which everybody usually uses. But obviously that's kind of dangerous. If you touch it, you will blow something out on the board if you short the leads across the capacitor and everything. But let me just go across this capacitor right fast. Black on the negative side, the big filter capacitor, since we have two. And then make sure your meter's in DC voltage. Check that. You see, we are 392 volts. All right. But back here, we're at 124 volts. Okay. So, for the capacitor, we have 392 volts, correct? Here, across the filter capacitor, 392 volts, 92 volts DC. But here we had 125 volts DC. How'd that go up? Power factor correction circuit, okay? As you can see, like I said, it amplifies the voltage. Yeah, what I'm trying to say, it amplifies the voltage, or it brings it up to a level where, you know, it could use the 300 and some volts. So it actually boosts it up to 392 volts because of this circuit right here. Now, how do we find out where the power factor correction circuit is? Easy. The power factor correction circuit, located here. Okay, right here. So this will actually boost the voltage up. Will boost the 125 volts to 392. Okay, all right. So, as you can see, it says PFC. All right, so basically what they use is a transformer right here, which is normally just a big inductor. Okay, it looks like a transformer on the board. And they also use a FET, transistor FET. Some components just may use an IC chip. That's it. And they also need something to drive the FET, which is usually an 8-pin IC. Okay, so that can drive the gate of the FET to actually cut the voltage on and off here and produce voltage. But on any TV, okay, that's why they call this a switch mode transformer, a switch mode power supply, because it switches these transformers, see one here, one there, on and off very fast using a FET and a driver IC to drive the FET, to cut the FET on and off, and that's going to produce energy inside of the windings in the coil, and thus it's going to transfer to the other side of the coil, right? And it's going to produce voltage, right? Which then has to be rectified and turned into DC or whatever. I'm sorry, it will turn into a regulated voltage. Same thing here with the main transformer here, main switch mode transformer. It's going to use a FET, right? And also a IC. Now the voltage that's driving this transformer is usually called, the main transformer is usually called a chopper circuit, okay? Same with this one also. Okay? Any transformer here. Okay. Now the way that you can tell which one is the PFC circuit, or the transformer for the PFC circuit, is the one that is transformer that is not isolated. Like on this one. Can you tell which one is for the PFC transformer? Right here. As you can see, these other two transformers are isolated. We got one side going to cold ground and the other side in the hot ground, the primary side. Same here. Cold, hot. The only thing, as you can see, this has the hot side of the board and the cold side has no electrical connection. Okay, that's why they use that switch mode transformer. Okay, because it's isolated, right? Okay, only thing here is these photo opto ICs, okay, which, you believe it or not, it's not an IC, it's actually a photo transistor. There's an LED, okay, like the ones you see me replacing in the TVs, inside of here, and on the other side of this optocoupler is a transistor, a photo transistor or whatever, right? And that's what, you know, takes the light and it tells the primary how fast to switch this transformer via the FET and the driver IC, okay? So that's what they use this for, the feedback, okay? As you can see on this one, okay? This is tapped to it's tapped to all of the voltage lines, right, or the rails after it's rectified, and it's going to tell the primary side. So this light right here, this LED right here, shines, right? Shines or flickers, depending on how fast it shines, how bright or how fast, depending on the voltage that's coming out here on the secondary side, and it's going to tell the primary side to either increase the switching of this FET or decrease the switching of this FET, okay? Or just to cut the drive circuit off, period, okay? Except there's a short or something, a bad short, it's going to cut the drive circuit off, period, okay? And that's why they use that photocoupler, because it has to be isolated, right? So there's no electrical connection inside of the photocoupler. It's just using a light. So everything's isolated. But like I said, power effective correction IC is right here. You see, it's all on the primary side of the transformer. Let me see if I can find another one here. This one right here, okay? As you can see, this main switching transformer, these pins here are on the cold side, the secondary side, and the primary side is here. So the PFC transformer is right here. Okay? And let me see if I can actually just show you. Here's a one drawing right here of a PFC circuit. All right. Okay. So evidently this is the FET. Okay. As you can see, it says boost PFC, right? This is the driver IC, this is the FET, okay? This is the voltage coming out of the bridge, this is the bridge rectifier, okay? Voltage coming out, going across this coil. The other side is being driven by this FET, all right? So it actually takes this voltage here, 120 volts, and by the time it gets here, past this diode to the capacitor right here, this is the main filter capacitor right here, it's gonna be 300 volts or 400 volts, whatever, how it's made. So, how do we find out the circuit? It's very easy. It's going to be by the PFC transformer. Okay? So, let's see. So I showed you on this one, right? PFC transformer. So, what are we going to do is we're going to flip it over. Okay? Once again, this is our PFC transformer. All right? And if we follow one of these pins, we should lead us right to the FET. Right here. That's the FET. That's the diode. Okay? FET, diode next to it. Okay? Now this should be going, put my meter in beat mode. We can also double check it like that. I'm gonna go to the drain of this FET and see? And this is our PFC transformer right here. So that is our circuit. And this obviously right here would be the driver for this FET to switch it on and off. For the PF circuit, not for the main transformer, okay? Just for the PFC transformer to help boost the voltage, right? And if it's on here, I'm going to find the transformer. Let's see where we're at. Okay, this is our primary side right here. This one actually uses two transformers. Okay, as you see, these transformers here are all on the primary side. So that would be our PFC circuit. And here are the FETs here. One should be a diode, okay? And the other one's a FET. And if we look on the back, we can see that they're probably using this IC right here, okay? To drive the FETs right here, okay? Drive the FET, which in turn is gonna drive these transformers right here. Okay, so we need that boost to boost the voltage up. So we have the voltage, the boosted voltage, ready to be used.